All right, now in section 6.4 called Solving Congruences, and we're also going to look in this video at section 4.5 on applications of congruences. We first look at linear congruences. What is a linear congruence? So a linear congruence are congruences of the form AX is congruent to some number B mod M. Now we have never had a number in front of X in a congruence before like this, but it's comparable to an algebra equation like AX equals B, where we just want to get rid of the A, and then we have solved the congruence or the equation for X. X is our variable that we're trying to solve for, all right? And what we're trying to find is all values of X that would satisfy this congruence. Now, how do you eliminate the A there? You can't just divide both sides by A, all right? Especially if the greatest common divisor of A and the mod M is not 1. If the greatest common divisor of the A value and the M is not 1, then you cannot divide both sides by A. All right. So what we need is what's called the inverse of A. And let's look at Theorem 1 to see how to do this. If A and M are relatively prime integers, so you got to have A and M to be relatively prime, and M is greater than 1, then a unique inverse of A mod M exists, and it is denoted as A with a bar over top it. That's the inverse of A. And the inverse of A has to be less than the mod number. So we're looking for some number less than the mod, so it's the inverse of A. Now, the statement here in yellow, thus A times the inverse of A is congruent to 1 mod M. So that's what you're trying to find, a number that when you multiply it by A will produce a remainder of 1 when it's divided by M. That's what this is. All right, so the product of A and its inverse should be congruent to 1 in mod M. Okay. Now, finding the inverse of A when A is small is often easy. You just need to find a K so that A times K is congruent to 1 mod M, and then K will be your inverse. Okay. So here's an example. Find the inverse of A when A is 3 and M is 5. Well, if you try 2 times 3, well, 2 times 3 is 6, and 6 is congruent to 1 in mod 5 because the remainder when you divide 6 by 5 is 1. All right? So right there we found it. 3 times 2 is congruent to 1 mod 5. So 2 is our inverse value. All right? Now 7 would also be an inverse value for this. What's 7 times 3? It's 21, right? 21 has a remainder of 1 when you divide it by 5 as well. So I knew that because any number that's congruent to 2 mod 5 is also going to be an inverse. Okay, but we only want one inverse, so we don't have to find other ones. Now, example 2 on page 276 shows how you can use the Euclidean algorithm to work backwards to get what are called benzoate coefficients that will help you find the inverse of A. So let's look at a similar example to this. Oops. All right, so here is an example where the problem says find the solutions of the linear congruence 13x is congruent to 6 mod 37. Okay, so what we have to do is eliminate that 13. But so we need to find the inverse of 13. So here's how you can do it. Now the Euclidean algorithm says that if we divide 37 by 13, first of all, 37 divided by 13, well, 13 times 2 is 26, and then you add another 11, you get to 37. So the remainder when you divide 37 by 13 is 11. And then you go on and do 13 divided by 11. Well, the quotient is 1 and the remainder is 2. And then you do 11 divided by 2, and so the quotient is 5 and the remainder is 1. And then you keep going. 2 is 1 times 2 plus 0. And as soon as you get that 0 remainder, then zero remainder, then you can start working backwards. Now, like I said, that example does this as well, but I'll show you what I mean by working backwards. So you start at the 1, because we want 1. Remember that the number times its inverse is congruent to 1 in the mod. So that's what we want. We start at 1. Now you don't want to get rid of the 1. You just want to start getting expressions that are equal to 1. So you see in this equation, I could subtract the 2 times the 5, and so it would be 11 minus 2 times 5. Now you don't want to multiply 2 times 5 and get 10, because what we're going to be doing is replacing the 2 and replacing the 11 with numbers that eventually get us to 13 and 37. Okay, so I'm going to systematically replace the numbers above the 1. So I need to replace the 2 and I need to replace the 11. All right, so I've got 11 minus 2 times 5. I'm going to replace the 2 using the equation right above it. If I subtract 11 times 1 from 13, so 2 would equal 13 minus 11 times 1. So I replace the 2 with 13 minus 11 times 1. Now don't multiply 11 times 1. What we're trying to get everything in terms of 11 and 13. Okay? And then eventually we'll get everything in terms of 13 and 17. I'm sorry, 13 and 37. Okay, so I have this. Now distribute the 5. You see the 5 on the right side? You distribute the 5 into both of these things. And this is going to be a negative of everything as well. So 5 times negative 1 and 13, that would make negative 5 times 13. Now don't multiply them together. Again, you want to keep your things so everything's in terms of 13s and 11s. So 5 times the negative 1 times the 13, so that'd be negative 5 times 13. And then 5 times the 1 and the negative sign, so that's, oh, and then there's another negative on the outside. So you're going to have a negative of a negative, so that's positive, and then times 5. So that's positive 5 times 11. But we're not done, because the 11s I could combine. I've got 1 11 here and 5 11s here, so that's 6 11s and minus the 5 times the 13. So we've got everything in terms of 11s and 13s. Okay. Now we're going to make a replacement for the 11. So using the top equation, 37 minus 13 times 2 is equivalent to 11. So using 11 equal 37 minus 13 times 2, I'm going to replace the 11 right here. Okay, replace this 11 with the parentheses. So 6 times 37 minus 13 times 2, and then you have the minus 5 times 13. Now 6 times 37, you write that down. You go 6 times the negative 2 in this term, which is negative 12 times 13. And then you have the minus 5 times 13. Now these 13s you can combine. A negative 12 13s and negative 5 13s will give you negative 17 13s. So you have 6 times 37 and negative 17 times 13. Now you wanted it in terms of 37s and 13s, which is your two numbers that are the A and the M. You wanted it in terms of those, okay? So we are done with working the Euclidean algorithm backwards, and we have found what are called the benzoate coefficients. Okay. Now, what do you do with that? All right. Well, since 1 is equal to 6 times 37 minus 17 times 13, and also 37 is congruent to 0 mod 37. Okay. Well, in mod 37, 37, what's the remainder when you divide 37 by 37? It's 0, so it's congruent to 0 mod 37. So I can replace the 37 here with 0 in mod 37. So the 6 times 37, that becomes 6 times 0, or that disappears, in other words. So in mod 37, I can say that the negative 17 times 13 is congruent to the 1 in mod 37. Okay, it's all because 6 times 37 is a multiple of 37, so it's going to disappear. All right, so negative 17 times 13 is congruent to 1 mod 37. That means that negative 17 is an inverse of 13. Remember when two things multiply together and are congruent to 1 in the mod, that they are an inverse? So then we now have a way to get rid of the 13. If you multiply both sides of that original equation by negative 17, okay, and I could have used positive 20 also, because negative 17 and positive 20 are both congruent to each other in mod 37. Okay. Anyway, I just used negative 17 and I multiplied it on both sides, as you see here. And so on the left side, that becomes 1, because we know negative 17 times 13 is congruent to 1 in mod 37. So that becomes just 1x. On the right side, negative 17 times 6 is negative 102. But you could add multiples of 37 until you make that positive. Okay, so if you add just 3 multiples of 37, that makes it positive 9. So a solution then is positive 9. Okay, and to check this out, you can plug it into the original equation. Go 13 times 9. So that's, I think 100 and, wait a minute, 90 and, okay, 117. And 117, is that congruent to 6 in mod 37? Well, 117 divided by 37, I believe you do get a remainder of 6 in mod 37. Now, other numbers possible are 46, 83, etc. All we have to do is just add 37 to 9 and then add 37 again, and you can just keep getting more and more solutions to this equation, but you only wanted one solution to this equation. Now, we're going to use what we just learned, but also use some more simple ways of solving a linear congruence to solve what is called the Chinese remainder theorem problem. Okay, let me go to the next slide and I'll show you what this typical type of problem is that you would use this for. Okay, here's a typical problem that you might use this for. When a class in a 500-seat auditorium forms groups of 7 students, there are 3 students left out. If you try to make groups of 9, there are 2 students left out. If you try to make groups of 11, there are 4 students left out. How many students are there if that's the case? Now, this is a typical Chinese remainder theorem problem. It gives you the remainder when you try to divide a number by, you know, some different numbers. Now we don't know. It's not, the class doesn't have 500 in it. That's just the capacity of the auditorium here. But this is a typical problem, because when you're forming groups of 7 or groups of 9 or groups of 11, that's like dividing by 7 and the remainder is 3, or dividing by 9 and the remainder is 2, or dividing by 11 and the remainder is 4. So this is a typical Chinese remainder theorem problem. But first, let's look at the Chinese remainder theorem and how it works. So Theorem 2, the Chinese remainder theorem, says let M1, M2, etc., all the way to Mn be pairwise relatively prime positive integers. So you could use 7, 9, 11. You just can't have them have any common factors. So they're all pairwise relatively prime. And all of them are greater than 1. And A1, A2, etc., all the way to AN are arbitrary integers. Okay, so they're the remainders, actually. All right, then the system, X is congruent to A1 mod M1, X is congruent to A2 mod M2, etc., all the way to X is congruent to AN mod MN, has a unique solution modulo the product of the mods. So if you multiply all the mods together and make a new mod M, this solution to the system it'll be a unique solution in mod M. Okay. Now any other solutions to this are congruent mod M to that original solution. Okay, so once you have one solution, all the other ones you can just add M to it to get the next one. Now the steps to solving a situation using the Chinese remainder theorem for 3 congruences anyway. In other words, yeah, three of these congruences here are the following. Write the facts of the situation in the form X is congruent to AI mod MI for I equal 1, I equal 2, and I equal 3. Verify that the moduli are pairwise relatively prime. So all the M's have to be pairwise relatively prime. If that's the case, and you can, get the facts into that form of, X is congruent to whatever, then it fits the Chinese remainder theorem. You can use the Chinese remainder theorem. Now, write the first congruence as x equals m1t plus a1. Now, m1 is the modulus, and the a1 is the remainder. So m1 is like the quotient, or I should say t is like the quotient, and a1 is the remainder. All right. So you've come up with an equation for x, an algebra equation instead of a congruence. Then you substitute this into the right side of, substitute the right side of this, the m1t plus a1, into the next congruence for x. So that'll be substituted on the left side where the x was. And then you solve for t in that congruence. Okay? So once you've solved for t in that congruence, then you can make another equation, and this time for t, where you write m2 times some other variable u plus a2, okay, using the second congruence, and then substitute that into the right side of that into the x equation and solve for u. So in the third congruence, u equals m3v plus a3, and substitute this into the previous equation with x to get x equals, now eventually you'll get x equals m1, m2, m3 times v. So, and then whatever the remainder is on the end is the solution. Okay, so this is a little tricky to explain. I've tried to lay out the steps, but we'll have to see it in the next in the example. I have two examples in this lecture. So again, so a problem will be presented in this kind of way. When a class in a 500-seat auditorium forms groups of 7 students, there are 3 students left out. If they make groups of 9, then 2 students are left out. If in groups of 11, 4 students are left out. How many students are there? Okay, so the statements can be written as x is congruent to 3 mod 7, because 3 is the remainder when you divide by 7. X is congruent to 2 in mod 9, because 2 is the remainder when we divided by 9. And x is congruent to 4 mod 11, because when we divided by 11, the remainder was 4. Okay, so the moduli 7, 9, and 11, we can see that they're all pairwise relatively prime. I know that 9 is not prime, but the only factors of 9 are 1 and 3 and 9, and 3 and 9 are not factors of 7 nor 11, so these are all relatively prime. Okay, now using substitution, we can reason as follows. The first congruence can be written as x equals 7 times some quotient plus the remainder of 3. Okay, that's how we got that equation. 7 is the thing we're dividing by because it's in mod 7. And the quotient is t. We don't know what that is, but plus 3, the remainder. Now we'll substitute that into the second congruence here on the left side. So 7t plus 3 is congruent to 2 mod 9. Now, just like in algebra, when you're trying to solve this type of congruence, you could subtract 3 from both sides. You can always subtract or add to both sides. So if I subtract 3 from both sides, I get 7t is congruent to -1. But in mod 9, I could always add a multiple of 9, okay? And doesn't change anything, because the remainder when you divide 9 by 9 is 0, so it's like adding 0. So I can add 9 to the -1, and it's like adding 0, and I don't have to add it to the left side because, like I said, it's like adding 0. So if I add 9 to -1, I get 8. So I get 7t equals 8. But if you keep adding 3 more 9s, you get to 35. Why would I want to get to 35? Well, I have 7t and I want to get rid of the 7. And if both 7t and 35 are multiples of 7, I could divide both sides by 7. But this can only be done if 7 and 9 are relatively prime. And they are, since the greatest common divisor of 7 and 9 is 1. So 7 and 9 are relatively prime. So, so I can divide both sides by 7, and I get just t is congruent to 5 mod 9. Okay? So if the thing you're dividing by and the mod are relatively prime, you can divide both sides by that number. So I get t is congruent to 5 mod 9. Okay? All right, now we use this to make another equation. T is our number on the left side, and 5 is the remainder when we divide by 9. So I can say t equals 9 times some number we don't know, so we'll call it u, plus the remainder of 5. T equals 9u plus the remainder of 5 for an integer u. Okay, so we just don't know what that integer is. All right, then we're going to substitute that, the 7u plus 5, into the equation we had up here, x equals 7t plus 3. And what we're trying to do is basically get rid of the t variable so we don't need it anymore. So since t is equal to 9u plus 5, I substitute 9u plus 5 for t into this equation up here, and I get x equals 7 times 9u plus 5 plus 3. And if you distribute, you get, and add the 3, you get 63u plus 38. Okay? Now, we haven't yet used the third congruence. X is congruent to 4 mod 11. So now we're going to substitute this, which is equal to x. X equals 63u plus 38. I'm going to substitute that into the third congruence in place of x. So 63u plus 38 is congruent to 4 mod 11. All right. Now, there's various ways that this can be done. I could subtract 38 from both sides, and I'd have negative 34 on the right side, and then I'd just add, you know, a bunch of the mod multiples. But I chose to do it this way. I know 44 is congruent to 0 in mod 11, right? Because 44 is divisible by 11. 44 is a multiple of 11. So it's congruent to 0. So I could add 6 to both sides to make this a 44. So that's what I did here. 6 added with this is 44. And on the right side, 6 added with 4 is 10. So I get 63u is congruent to 10 mod 11. Now, to get rid of that 63, all right, let's see, how do I, what I did here now is realizing that 55 is a multiple of 11. So 55 is congruent to 0. And so 55 times u would be congruent to 0, because this is congruent to 0, so times u is 0. So 55u is congruent to 0. And then if we subtract 55 u's from 63 u's, you get 8 u's congruent to 10. Okay, So there's a lot of ways you can change a congruence and get it lower into lower terms and simplify it a bit. But so what we have to do somehow though is get rid of that 8. Okay. Well, I can see that the number I'm trying to divide by, the 8, and the mod 11 are relatively prime. The GCD of 8 and 11 is 1. So we can divide by 8, but first let's add 22 to the right side because 0 is congruent to 22, mod 11. So if I add 22 to the right side, I get 32. So 8u is congruent to 32 mod 11. And since 8 and 11 are relatively prime, I can divide both sides by 8. So I get u is congruent to 4 mod 11. Okay. So that as a statement then is u equals 11v, because the mod is 11, so it's 11 times some quotient plus the remainder of 4. All right. Now we have been trying to get all along. We have been trying to get rid of these other variables and eventually get to the point where, excuse me, we can bring it all together. And so what we're going to do is substitute. We know u is equal to 11v plus 4, and we can plug that into the equation that we had up here, x equals 63u plus 38, and substitute it in there. So 63 times u, but u is equal to 11v plus 4, and then plus the 38, and distribute the 63 and add the 38 to it, and you get 693v plus 290. Now 693 is 7 times 9 times 11. So that's the product of all of the mods. And that's what you were trying to reach. You're trying to reach it being in that x equals 693v plus 290. You needed to have that number 693 in front of v. All right. So that means that the remainder, when you divide by 693 or mod 693, is 290, and so that's what we wanted. So x equals 290 mod 693. All right. So the answer to this problem is 290 students. Okay. Now, what if the auditorium could only hold 200 students? Well, then this would be an impossible problem. All right. Here's another question. What if the auditorium could hold 1,000 students? What would that matter? Well, the mod is 693, right? If I added 693 with 290, that gives you 983 students. And that is a possible second answer. So there's there would be two answers to this problem, either 290 students or 983 students. Okay? Because we could always add another mod to get another solution. And the mod is 693 here. All right? But because the auditorium can only seat 500 and not 983 students, then we only have one solution to this. Okay? So let's look at another problem, and I've tried to organize it a little bit better this time, so you can see what's happening here a little bit better. So here's an example. I have cash in $1 bills, let's say, but it's less than $400. So that's like the 500 seat auditorium limit, the limit there. 400 is our limit in this case. If I put it in piles of 5, there are 3 bills left over. If I put it in piles of 7, there are 2 bills left over. If I put it in piles of 8, there are 5 bills left over. Okay, so the leftovers are the remainders, of course, when we divide by however many will be in the piles. So we first write the statements as x is congruent to 3 mod 5. So because you have 3 left over when you divide it by 5. X is congruent to 2 mod 7. When you put it in piles of 7, you have a remainder of 2. And then x is congruent to 5 mod 8. Because when you put it in piles of 8, you have 5 bills left over. So here are your congruences, okay? The moduli, 5, 7, and 8, are all pairwise relatively prime. There's no common factors between any two of the moduli, except for 1, of course. And the product, 5 times 7 times 8, is 280. All right. Now, let's see this worked out here. All right. Now, first, using the first congruence, x is congruent to 3 mod 5, means the remainder is 3 when you divide by 5. So I could write this as x equals 5 times some integer t plus 3, the remainder of 3. Okay. Now I'm going to take that expression and stick it into the second congruence. So in place of the x, I put 5t plus 3 is congruent to 2 mod 7. All right. Now if I subtract 3 from both sides, I get 5t is congruent to negative 1 mod 6. I'm sorry, mod 7. And if I add 7 to the negative 1, because we're in mod 7, 7 is congruent to 0 mod 7. So if I add 7 to the negative 1, it's positive 6. And so it gives me a positive number here on the right. So 5t is congruent to 6. Now, in mod 7, 14 is congruent to 0. So I could add 14 to this to make it 20. And so 5t is congruent to 20. Now, why did I want to do that? Because now I can divide both sides by 5, but I can only do that because the greatest common divisor of 5 and the mod is 1. And so I can now divide both sides by 5, and I get t congruent to 4 mod 7. All right? So we've broken this congruence, or we've solved this congruence for t. But now we use that congruence, t is congruent to 4, to say t is equal to 7 times some integer u plus the remainder of 4. Okay? The remainder of 4. Now, I now substitute this value, this expression for t, into the first equation that we wrote here. X is equal to 5t plus 3. And here's this where I did that. So x equals 5 times 7u plus 4 plus 3, which gives you 35u plus 23. All right. So now we have that x equals 35u plus 23. Now we go to the third congruence, and I substitute that 35u plus 23, which is equal to x. I plug that in for x, and so I've got 35u plus 23 is congruent to 5. All right. Now, I add 1 to both sides because I see that 23 is almost to a multiple of 8. Almost to a multiple of 8. So why? Because it's in mod 8. And if I add 1 to both sides, I get 35u plus 24 equals 6. And 24 is congruent to 0 in mod 8. So I can just eliminate that 24. I can replace it with 0. So now I get 35u equals 6. Okay. Now, what did I do next? Well, any multiple of 8 is congruent to 0. And so 35, if I subtract 32 u's from 35 u's, why can I do that? Well, 32 u's, 32 is congruent to 0. And so I'm not really subtracting anything from the both sides. I'm just subtracting 32 u's, which are congruent to 0. And so I get 3u is congruent to 6. Now, my number 3 here and the mod 8 are relatively prime. The GCD of 3 and 8 is 1. So I can divide both sides by 3, and I get u is congruent to 2 mod 8. Okay? But like I said, there's lots of different ways that you could do that. But you can always replace a multiple of the mod with 0. So now, taking this congruence, u is congruent to 2 mod 8, I know that when I divide u by 8, the quotient is v, let's say, plus a remainder of 2. So I can write u equals 8v plus 2, all right? And then I'm going to put that into my equation x equals 35u plus 23, the previous equation for x. And I'm going to replace the u with 8v plus 2. So that's what I did here. 35 times 8v plus 2 plus our 23 on the end. And you distribute there and simplify, and you get 280v plus 93. Now, how do I know I'm done with this process? Well, I've reached my 280 that I wanted. I want the product of all the mods, 5 times 7 times 8, which is 280. I want that in my expression, and then whatever's on the right side of that, in other words, the remainder on the end, is going to be the answer. Now, so what this says is that x is congruent to 93. In other words, the remainder is 93 mod 280 when I divide by 280. Okay. Now, this problem, though, allows for a second answer, second possible answer. If you add 280 to 93, you get 373. That's another possible answer because all we know is that it's less than $400. And 373 is less than $400. So there are two possible answers. You could have 93 $1 bills, or you could have 373 $1 bills. So it's impossible to tell which of the two it is because it could be either one. So there are actually two answers in this case. So I hope that helped in the way it was arranged so you can see more clearly what's going on. In the previous example, it was all in one big paragraph without any order to it. But maybe this will help in your understanding of it. Now, another aspect that uses the Chinese remainder theorem is a result that is called computer arithmetic with large integers. And it's not really a theorem, but it's just a fact that if m1, m2, etc., all the way to mn are pairwise relatively prime moduli, and m is the product, so m, just like in the Chinese remainder theorem, m is the product of all the moduli, then by the Chinese remainder theorem, an integer a with a between 0 and m can be uniquely represented by the n tuple consisting of its remainders upon division by mi for I equal 1, 2, 3, etc. That is, we can uniquely represent a by A mod M1, A mod M2, A mod M3, etc., all the way to A mod Mn. So let's look at an example and see what this is talking about in a more concrete way. The example says, find the pairs used to represent the non-negative integers less than 10 when the component of the pairs is the remainder upon division by 2, and the second component, when the first component of the pairs is the remainder upon division by 2, and the second component is the remainder upon division by 5. Okay? So, what we're seeing here is what we're trying to do is take the non-negative integers less than 10. So, starting at 0 and ending at 9. And if you represent them as pairs of remainders when you divide by 2 and you divide by 5, then these pairs are unique. Okay? So 0 is, the remainder when I divide 0 by 2 is 0, and when I divide 0 by 5, it's 0. The same thing with 1. When I divide 1 by 2, I get a remainder of 1. And when I divide 1 by 5, I get a remainder of 1. But in the next case, 2 is 0, because if I divide 2 by 2, I get a remainder of 0. And then if I divide 2 by 5, I get a remainder of 2. Anyway, so you can see that the first number in each pair is going 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Because if you're dividing by 2, if it's an even number, you come out with 0. If you divide by 2 when it's an odd number, you get a remainder of 1. But then the multiples of 5 are, when you divide by 5, you can either get a remainder of 0 or 1 or 2 or 3 or 4. And then it repeats again, 0, 1, 2, 3, 4, etc. Now, why did we choose 2 and 5? Okay, well, we could have used other numbers, like we could have used 3 and 4 when you divide by 3 and 4, because these could be uniquely, so if I use 3 and 4, then our moduli are 3 and 4, and the product of them, m, would be 12. And if I'm doing 10 integers, well, 10 is less than 12, so that would work, okay? But you couldn't do 15 integers all the way up to 15 if you're using 3 and 4. You could only do up to 12, okay? Now, 2 times 5 is 10, so I had exactly all the pairs possible that are used in this case. All right. So this is interesting because situations that you might want to use smaller numbers to define larger numbers. All right. So you can also see example 7, page 279. Now, an important result that comes from some of these things we've been looking at is Fermat's little theorem. Now, history tells us that Fermat wrote this theorem in the margin of one of his other, papers. They used to write letters to each other, but he wrote this in the margin and said something about him having a proof of it, but it's too long to put here in the margin. Took a while before other mathematicians proved it, but it's an interesting little proof. interesting little theorem. It says if P is prime and A is some integer not divisible by P. So you cannot have the integer A divisible by the prime number P. Then A to the power of P minus 1 will be congruent to 1 mod P. All right. A to the power of P minus 1 will be congruent to 1 in mod P. Also, if I multiply both sides of this by A, that will add 1 to the exponent here. And if you add 1 to P minus 1, you get P. And if you multiply both sides by A, on the right side it'll become A. So another way to write this same theorem is A to the pth power is congruent to A mod P. So A to the P power is congruent to A mod P. So let's look at an example, but you can also look at example 9 on page 281. But another example, if P is equal to 11, so 11 is a prime, A to the 10th power, so that's the P minus 1, so A to the 10th power will be congruent to 1 mod 11. Now that'll be true for any A value that is not divisible by P. And then A to the 11th is congruent to A mod 11. So that's the second version of it. For all A from 1 to 10. Now, that's because for all A less than 11, 11 does not divide in evenly into A. Okay? But it would work for, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But it won't work when A is 22. If A is 22, then 11 divides into 22, so it won't work if A is 22, if the P, the prime number, is 11, all right? But it'll work for all the other non-multiples of 11, okay? So interesting little theorem, and it's actually used in something in modern cryptology, which we're trying to lead up to here to help us understand the mathematics behind modern cryptology. And this is used in that. So a few applications of congruences are given in section 4.5. They are kind of interesting. If customer records are identified by some key K, such as a customer identification number, let's say every customer has an identification number, and that's called the key, or K, or maybe it's the customer social security number, whatever, then a hashing function h of k can be used to locate that customer's records at the memory location h of k by a function. So in other words, h of k is just a function used to locate where that customer's records are in the memory of the computer. All right. One of the most common such functions is h of k equals k mod m. So m is the number of available memory locations. Okay. Now, what does this do? This finds the remainder when you divide k by the number of memory locations. So it finds the remainder when k, the customer identification number, is divided by m. All right. Now, when two identification numbers, have the same remainder mod m, then you'd have some type of collision, okay? And what you have to do is somehow program a way to mitigate this situation. So to mitigate this, often a record is just assigned to the next available memory location using a linear probing function. Now, the linear probing function will probe the next available locations using this function here, h of ki. So it introduces this index variable that'll have a loop that it'll take it through one at a time and find an empty location. So h of ki is h of k plus I mod m. So it adds some index variable to it to go to the next location over. But this is called a hashing function. Now, another computer application is what are called pseudo-random numbers. Now, pseudo-random numbers are kind of fake random in that they're generated by some computer algorithm or function. But they look so random that they're practically, random for all of our purposes. So functions that are to generate numbers that appear to be random include the recursively defined function x of n plus 1 is equal to a times x of n plus c mod m. So it takes the previous random number x of n and multiplies it by a and adds a number c to it, and then finds the remainder when you divide it by m. So it takes and does this calculation and then divides it by m, and the next random number is the remainder when you divide that by m. Now you need to have your a value to be something above or 2 or higher, something from 2 to m. All right, so a is from 2 to m. C has to be from 0 to m. And x0, that's the starting value, has to be between 0 and m. All right, so that starting value, x0, is called the seed because it's like the beginning of the sequence of random numbers that you're generating. But the parameters a, c, and m and the seed x0 are chosen at the beginning, and then once this is told to proceed and keep generating random numbers, then you don't have to change anything. It just runs by itself, and these appear to be random. Okay, now if you divide each of these x's by m, you will generate decimal numbers between 0 and 1 that are random numbers all in between 0 and 1. So be like 0.7592013, it'd be really precise random numbers. Okay, and why do we do that? Well, we could just multiply by any number we want, and it'll produce random numbers between 0 and that number we multiplied by. And so it's convenient to adjust this if the numbers are generated between 0 and 1. Anyway, so often a linear congruential generator with c equals 0. All right, so in other words, we're going to eliminate the plus c thing. Means the only thing we're going to do is multiply by a and then figure out the mod with the remainder. So we won't add the c to it. We'll just go a times the number and then figure out the remainder. That's called a pure multiplicative generator. And it's often easier to do, and it's a little bit faster. But for example, the pure multiplicative generator with modulus m and multiplier a equals 7 to the 5th power. So in other words, we're going to multiply by a being 16,807. That's widely used. So our a value of 16,807 and our mod of 2 to the 31st power minus 1, which is a prime number, by the way, but it's a Mersenne prime. And so that is widely used. Within these values, it can be shown that 2 to the 31st power minus 2 numbers are generated before repetition begins. Now that's a pretty high number. So this repeats. This is a fairly simple random number generator that can repeat, 2 to the 31st power times before repetition begins. That's pretty good. All right, that's a lot of random numbers before you repeat any random numbers. Now, banks and other institutions use what are called check digits. These are to make sure that there wasn't any errors in transmission or human errors in typing in a credit card number or UPC code or an ISBN number. So it's to help us make sure that there's no error in transmission over the internet wires or an error in human typing of the number. All right, and a final check digit is added to strings to check for accuracy. Now, this could be a number like between 0 and 10 that's added on the end, or it could be a 1 or a 0 added at the end to check for accuracy. Now, if it's a 1 or a 0, we call it a parity check bit. It's a single 1 or 0 added to the end of the binary string, and this check digit is one more than the number of digits you have in the string, so it's added at the end of it, and all you do is add up all the digits and then find the remainder when you divide by 2. So if the sum of all these digits from x1, x2, x3 all the way to x of n is an even number, then the parity check bit will be 0. If the sum of all those ones and zeros is an odd number, then the parity check bit will be 1. Because what's the remainder when you divide by 2 of an odd number? It's 1. So that way, on the end of the line, when you receive the string of zeros and ones, it can add up all the ones and zeros except for the last 1 and 0 and see if that's an odd or an even number, and then see if the parity check bit on the end matches. Okay, and what it can do is check if a single digit was changed. So if one of the ones or zeros got changed to the opposite of what it was, it'll find that error. But what if 2 ones are changed? Or let's say a 1 is changed to a 0, and then a 0 is changed to a 1. Well, one change made up for the other change, and so the parity remained the same. It was still even if it was originally even, and it's still odd if it was originally odd. So therefore, it couldn't detect it. So if you have 2 errors, it doesn't detect this. Now, look at example 4 on page 290 for a more understanding of this. Now, universal product codes, UPCs, they use a check bit generated using modulus 10 according to the function 3 times x1 plus x2 plus 3 times x3 plus x4 plus 3 times x5 plus x6, etc., all the way to x12. And then it calculates that in mod 10. All right. So why did it do this this way? Why do they have 3 and then 1 and then 3 and then 1 and then 3 and then 1 for those coefficients on this? Well, that way, if a person typing in a product code, UPC code, had transposed the digits, okay, transposed the digits, then you would be able to tell, because you're multiplying 3 times the x3, but only 1 times the x4, and so if I switched what x3 and x4 were, it would tell whether it would be able to tell the error, because the final sum of all that would not be the same mod 10, same remainder when divided by 10. ISBN numbers, oops, use a check digit generated by the series x of 10. So that's like the 10th check, the last digit of a ISBN number that's 10 digits long. The last digit is found by going the sum of all of these here. Okay, what are these terms? Well, it takes the index variable I and multiplies it times x of I, which is the digit for that place. And then it adds to that, just like in the previous example, it added up all the things. Well, this is adding up all those things, okay? But it uses mod 11. Now, it has to use mod 11 because the sum of all this is going to be congruent to 0 all the time. But anyway, long story short, so that last digit, if it equals 10, if the sum of all this equals 10, then you write an X at the end of the universal product code. I'm sorry, the ISBN number. So here's an example. Find the 10th digit for an ISBN number that begins with 006320472. So notice there are 9 digits there. Excuse me. All right. So we use this expression in mod 11, and I go I, which first case I is 1. So 1 times x1. Now x1 is the first digit, which is 0. So 1 times 0. And then it does I again, being 2 this time. So 2 times x2. Well, x2 is a 0. And then 3 times the x3, which is 6 this time. So 3 times 6 plus 4 times x4, which is the 3 here. So 4 times 3. And then 5 times the x5, which is 2. And then 6 times the x6. Well, x6 is 0, so we got 6 times 0. And then 7 times the x4. I'm sorry, 7 times the x7, which is 4, and then 8 times the x8, well, x8 is 7, and then 9 times the x9, and x9 is 2. So if you add all that up and figure out what that is mod 11, it comes out to 10 mod 11. In other words, when you divide that big number, you get, when you add all that up together, if you divide that by 11, the remainder is 10. Okay, now up in this explanation of ISBN numbers, it said use X to represent 10. So that last digit will not be a number, actually, it'll be the letter X. And so if you've ever seen ISBN numbers that end in an X, that last digit is not really part of the number, it's just a check digit. So that when you type it in, it'll check to see if you've typed it in correctly. Okay. Now, these methods can detect single errors, typos, or transposition errors when you have switched 2 digits. All right. So that was quite a long lesson, and it had to do with solving linear congruences, something you need to practice, using that to do Chinese remainder theorem problems. And then there were also applications of congruences. Those are fairly easy once you have that those ideas down. Of course, you can use your notes, so you might want to print them out and have all that with you. But these are interesting applications, and it's important for a computer technology uh, uh, professional to have an understanding of things like check digits in UPC codes or ISBN numbers or whatever. So hopefully that was helpful for your understanding in these areas. The next video is on cryptology, and it's very interesting, computer security.